Okay, so we're gonna do Codechef Starters 155. So I'm gonna go over from the first four problems. So from GCD to 1, replace with verse, prefix, suffix, min-max, and array concatenation. Which I will almost solve this one, but didn't. And then this one I'm not gonna do, although I have a feeling it's actually almost the same level of difficulty as this array concatenation. Start from the first one, or hold on, yeah. So GCD to 1 hard. It says construct a matrix A of size n times m such that the GCD of every row and column is 1 and the sum of elements of matrix is minimized. The element must be between 2 and 10 to the 9. If there are multiple answers possible, print any. So key thing here is that you have to minimize the sum. So you're going to want to use like the smallest numbers possible. Also, like the thing I misread originally is that you want the GCD of every row and column to be 1. So for each row and column, you want it to be 1. So um, essentially, my approach is in order to get a GCD of a row to be equal to 1, you have to have two numbers that are coprime. And since you can start from a 2, you're probably like, let's just look at a row, a one-dimensional array or something. So it only has one row. So then if you place a 2, you're good. Like that's the smallest number. The only requirement is you have to place a 3 somewhere in here. And then the rest you'll do as 2s because 2 is smaller than 3. You'll minimize the sum of this if you use 2s. And by having this 3 here, you guarantee the GCD of this will be 1 because the 3 and the 2 are coprime. So the only thing you really have to guarantee is that in each row and column, so given the matrix, you have to make sure you have a 3 in each row and column. So then you just kind of figure out how to place them. And so what I'm doing is something like this is it places a 2 in every single cell, and then I just figure out where to place the 3s so that to make sure that the GCD of every row and column is a 3. So that means for each row we have to add in a 3. So how I do it is I just start from an index here, I, and then keep moving the index and placing the 3s. That way you're guaranteeing that you're getting each row and you're also getting a different column each time. And you can do this, and it can fill in if you have to, if your number of rows and columns are the same, it'll fill it in like this. But if this is more like something like that, something where there's more columns than there are rows, then it'll fill it in like this, and then it just has to start over. So it just has to go up here. That way, it's like yes, it's filling in double in this row, but it has to fill it in this column. So this is kind of what it would do. And then if it's the other way around, and it was like this, and the number of rows is greater than the number of columns, then you could go. Now you need to go back. You're going to place in multiple 3s in one column, but you have to do that to be able to fill in the rows. So that's another way. And okay. And so the easiest way to do this is just do these modulo R and I modulo C so that it will keep incrementing the row and column until, and then it'll wrap around once it gets too large. So like so like in this one where you have your rows and your columns, you'll keep putting the 3 and you keep incrementing your index, But at this point, I mod R will wrap around and go back to the start. But column will keep increasing. And then I'll do the vice versa for the other one. So I'll just show the code for this one. So it's basically that. You want to go whichever one's max, you want to fill in every single row and every single column, but just make sure you do this wraparound thing or this modular. Take the row modulus, the number of rows, so that it wraps around and starts over when it fills in all the rows, and do the same thing for columns, and then see out, and then that will solve this one. So hopefully that one's clear. I'm going to move on to problem B. Replace with first. So you're given two strings s and t of length n and m respectively. You can perform the following operation on any of the strings. Replace a substring with this first character. So a, b, c, a, b, c. You can replace the substring CAB with the first character in the substring, which is a C. You want to know what is the minimum number of operations to make both of the strings equal, or determine that it's impossible to make both strings equal. So, okay. So for this one, you kind of want to determine if you want to make the strings equal. And so like one thing I kind of look at is when would it take 0 operations? So if both strings are the same, it's going to take 0 operations. Okay, so that's simple. Then I ask the question is, when is it going to take 1 operation? Well, S and T. Or actually, before we go to 1 operation, because this one's kind of easy to argue, 1 operation might be a little more complex, but when is it going to be -1? That means it's impossible. Whenever whenever the first character doesn't match. Because the best you can do is you can convert this string into A and you convert this string into B, but they'll never be equal. You can never make these equal because the operation is basically like you take ABC and you can basically take this substring and then concatenate it, or not concatenate, but contract it into just what the first character is, which is A, which means that there's no way to change the first character in a string. There's no way to change these two characters, and they will always be the first character in both of these strings. And so they will never be equal. So that's when it's impossible. So then the question becomes, when can you do it in 1 operation? And okay, so when you can do in 1 operation, we'll give an S and T. So an easy example would be like A, B, C, D, E. Like this is an easy example where you can kind of see, oh, I can make them equal because I can just take this part and contract it into the C. So in this case, you can see it's 1 operation because the prefixes are equal. So you can just contract this one, and you can just operate on the T. Now, actually, for my problem, what I'm doing is, since S and T, you can operate on both S and T. One thing that I always do is I always make sure that S is my longer string. So actually, T would have been this one. But okay, it doesn't really matter. So that would take 1 operation. And you might say, okay, well, what if you have ABC and you have something where it's like ACC? Can you do this one in 1 operation? So no, you won't be able to do that one in 1 operation. But what's another one you can do in 1 operation is something like A, B, C, D, E, F, and then let's say you have another string here. You have A, B, C, L, D, E, F. So for this one, you can do in 1 operations. Why? Because the suffix of this matches this suffix, and the prefix of this matches this. That means that there is a. I did this in the wrong order. I meant S to be the longer string. Okay. So yeah, because I said I'm always gonna have S be the longer string, so I should do that. So S is this longer string. So there's a substring you can remove. Like basically, the operation you can perform allows you to remove a substring within a string. And so you can do this one in 1 operation because you just take this substring and contract it to the C, and that basically deletes this substring. Actually, that's another way to say it, is that you're able to delete substrings. But without being able to delete the first character. But you can do this. So in 1 operation, you can make this S equal to T. So that's another example of one operation. Um, so really, the only way you can do one operation is if you can somehow take this string, find a prefix that matches, and then remove the bit in between, and then see if you concatenate the prefix with the number of characters you need remaining. Like I need 3 more characters, so take the last 3 characters and see if it will equal to t. That's one way to think of it, but okay. So what about 2 operations? So 2 operations solves a lot of the problems really easily. So 2 operations is something like this. Something like this. So you can't do this in one operation because you don't have like a substring you can delete, right? Like the A characters are the same, which means it's not impossible to make these equal. These characters are the same, but these characters are not the same, and these characters are not the same. So you don't have any like suffix and prefix that match. Um, the only way to do it is to contract this into an A and contract this into an A. Basically contract them into the equal operation. So you can always make, since you can operate on both S and T, you can always get it in at most 2 operations. It would never take 3 operations. 3 operations would be worse than this. So yeah, essentially those are the main key points. Hopefully that's clear. So basically you say 0 operations of S and T are equal. Also here I make sure that S is always my longer string. And then here I check for the 1 operation, and then if 1 operation doesn't work, you just have to check that if the first characters are equal, you can do it in 2 operations at least. Otherwise, it's impossible. And then this check function just goes through and matches the prefix for as long as it can, and then creates a substring up to that prefix. So it basically takes the prefix of S, which is the longer string, and then it takes the suffix. It basically says how many characters remaining do I need. Take that from S, take those remaining characters, and then just see if this is now equal to the t. Basically, what this is saying is if I delete the characters in the middle from S, does that make it equal to t? Yeah. Or is there some substring I can delete that will make S equal to t? And this will find that, this algorithm. Okay, and then this one is where it gets maybe a little more abstract. So prefix, suffix, min, max. So you're given an array A with integer elements of size n. We create another array B where basically it follows this equation, which I will explain in more detail in a second. If you kind of write it out, it kind of becomes a little clearer. But basically, it's just saying that um, each element in array B, the ith element, is equivalent to the prefix sum of all of array A up to index I minus the maximum value from that prefix as well of array A. And then you're given this array B and asked to find any valid array A. For a given array B, the solution always exists. So you guarantee a solution always exists. And you can look at the constraints. They're not super helpful, but it does constrain you on A, but these are pretty large, so it's really pretty, don't have to worry too much about it. These are some examples. And in fact, I'll use one of the examples. I'll use this example actually. Yeah. Okay, so let's do this one. So what's this? Do white. Okay. So this is basically B. I mean, yeah, this is B, and you want to find what A is. So how I kind of started with this is I just said, okay, I'm just going to guess a value. This is kind of a constructive problem. So I just guessed a value for A1 and just said, set A1 to 0, whatever, right? It's like the most middle number between the two to the net, because A can be between negative 2 million to 2 million. So I'm like zeros between those. It's the halfway point. So So then if you want to solve this, you can just say, okay, well, now the first element is obviously a1 minus a1 equals 0. So like it kind of tells you that you don't care what a1 is. The first value, this first value in the B array constrains nothing, does nothing really. The only thing it really does tell you is for there to be a solution, the first value in B has to be a 0. Because no matter what, when you subtract a1 by a1, it will always equal 0. And so since it says there's always a valid solution, you can assume that B always starts with a 0. Okay, so I didn't give too much information. Then if we go to the next one, the -2 though, then that's saying that a1 plus a2 minus the max of a1, a2 is going to be equal to -2. Okay, well, a1 we already have is 0, so that doesn't really matter. So you have a2 minus the max of 0, a2. So first off, a2 is not going to be a max. Why? Because if a2 is a max, this would be equal to 0. If a2 was a max, this would be equal to 0. Because then you're just taking a2 minus a2. So that's not possible. So really, you're taking a2 minus 0 equals -2. So you can quickly see that, oh, a2 has to be -2. Okay, so everything's fine up to this point. Then if you want to solve for the next one, it's going to be -2 plus a3 minus 0. Let's say we're not going to make this larger because this isn't 0. And that has to be equal to 1. Okay, so you can take this to the other side, and you get a3 minus 0 needs to be equal to 3. Now we're in trouble here because this number is positive, that means that a3 has to be greater than our max. But if a3 is greater than our max, we're going to get 0, right? Because your max will be updated. This max will be max of 0 and whatever a3 is set to. So if you set it to 3, you're just going to be, you're going to get 0. So it turns out it's actually impossible. Starting with a1 to be 0, you can't possibly get a solution. So what I realized when I did this example is that I can't just pick any number for a1. You have to pick a specific number for a1 that allows this to be solved. So okay, so let's go back a little bit. So what did a1 actually have to be here? I'm actually going to try something. This is not what I did. I did it more of like an observation. I did more of like an observation to be able to solve this, but I'm going to try something maybe more, a different way of approaching it right now. See if that changes it. So if I take, what if I start from the end? I take a1 plus a2 plus a3 minus max of a1, a2, a3, and let's say this is equal to 1, right? So one thing is for certain. Remember, a1, we don't care what a1 could be, whatever, right? We don't really care what a1 is. But I kind of want to find what a1 is. And so a1 is going to be, also one other thing you can say about in here is that, okay, this may not be the most intuitive thing here. I'm still going to try. So you take 1 minus a2 minus a3 plus the max of a1, a2, a3. Okay, you could do that. So what you notice here is this here. So you're trying to solve for a1. You say a1 has to be like this. Okay. So what if your max value is just always a1? And this is kind of what I derived, although I derived it a different way. So if you say your max value is a1, then, oh wait, that doesn't really help here. Well, I mean, it means that, uh, yeah, no, it doesn't help too much here. Um, okay, yeah, I think I'll go back to how I actually did this. I think it made more sense. But I'm going to take a bigger example and just go through it. Yeah, I tried that, but that actually did not lead to something more intuitive than what I did this over here. Change this back to 4. Sure. Okay, so this is what I did. So I took this as the B. Okay, so I created some B array just as an example to work through. And it's valid because it starts with a 0. There's also another 0 in here. So, okay, so what you have to look at here is the only thing you're really interested in is basically a prefix sum and some max values. So again, if you choose, okay. Oh, this is unfortunate. Okay, that was disastrous. Okay, let's try this again. Oh, okay. Okay, so if you just try some A1 value, you just say A1 is equal to, I guess we could say A1 is equal to X, let's say. Or yeah, let's say A1 is not solved. But let's say A1 is going to be the max value, or now let's just say A1 to 0 actually. So what's going to happen in the very first instance is we're going to need to solve for this -1. So we're going to say 0 plus A2 minus the max. Okay, the max cannot be A2. So I'm going to say the max is just whatever 0 is. And so this has to be -1. So this is like your prefix sum, and this is like this. Okay, so A2 is going to be -1 in this instance. So then you're going to have -1 plus A3 minus 0 equals 1. It's like, okay, how could you possibly get this? I mean, you could get this because if you take the -1 over here, you're going to get A3 equals 2. And that is a possible solution for A3. Now, your prefix sum is -1 plus 2. So it's 1 plus A4 minus 0 equals 5. Now, if we take the -1 over there, we have A4 equals 4. So what's the problem here? Actually, the problem happened here, and I didn't even say it. Yeah, so actually, we'll use this example, but the problem actually happened here. This 2 is greater than the 0, so you actually would have done 2 minus 2, and it would have been 0. So it wouldn't have worked. So my basic insight was that if you track a prefix sum and track this, like yeah, if you just do that. So let's say yeah. So the prefix sum is like okay, trying to think, because I don't know if I know how to prove this one very well, but I'll try. So okay, prefix sum is like 0 initially, although that's not what it initially will be wherever you set A1 to. So I say you set A1. So when you take this prefix sum, if you look at the formula from before, you take your prefix sum plus whatever your current index is minus the max of, whatever. But the thing is that just remember the max, this AI cannot be your max value. So your max value would have to be A1 is what I'm arguing, because you can never see a new max value because it would just equal 0. Even though you could have 0, but you need to have numbers that are not 0 in here. And this equals some BI. So you can solve this for AI. And it's BI plus A1 minus P sum. And so the argument is that AI has to be less than or equal to A1. So how can you make sure of that? Again, why is that the case? Because if AI is greater than A1, it will set the value to 0. Like it'll mess it up. It won't allow me to like set a positive value that's greater. Like it breaks in this instance, we can say for sure. So with this constraint on AI, if we look at this, that means we're saying that this is the same thing as saying that AI minus A1 is greater than or equal to this. Okay. I mean, this here greater than this one. Yeah. Well, that means that this or this always has to be greater than this. See, I don't know. I'm not seeing the proof here, but basically the idea that I had was that take the maximum difference and just set A1 to that. Because I was just thinking intuitively, then you would never need to have something larger than that. Like the max distance here is 7 in this array. And I was just thinking you'll never need to set a value greater than 7. Because kind of like as you kind of go through this thing, like if 7 is your value, just remember the equation for AI is, I guess let's look at this equation with respect to this, minus P sum. But you're setting this to 7. So you're saying AI equals BI plus 7 minus P sum. And so if you think about what P sum is going to be equal to as you go through this array, it's going to be related to the 7, right? It's like it's going to decrease from the 7, but also it could increase above the 7. So for instance, in this one, the P sum here is originally 7 here at the first one. Then it's going to be 6 here, right? So then it's going to be 6. So then if you're taking BI plus 7 minus this, and you're setting AI equal to that, it's like, is AI going to be greater than 7? No. And then the P sum could be 7 here. And then the P sum could be, when you add 4 to it, it'd be 11. And then if you add 7 to it, it'd be 18. Okay, yeah, I'm doing this one live here. So the P sum is all the way up to 18 now. So just think about what that means. That means you've gone all the way to here, but you're taking 12 plus 7 minus 18, and like, what's this? This is 19 minus 18, right? Okay. I mean, 18 may be wrong, actually. I have to go back through this. Okay, yeah, so you have 7, 6, 7. You add 4 to that, you'll get 11. You'll add, oh, right. It depends on what your value is. Yeah. Okay, but I think you can kind of just, or you can do this. You can say this. You can say I set A1 to 7, and then set A2 to the value has to be. But just thinking about it, you know it's going to be -1 plus 7 minus p sum, which is currently 7. So yeah, you know it's going to be -1. And then A3 will be, so this will be adding 1, so it'll be 1 plus 7, but the prefix sum was 6, so I think this is just basically 0. And then A4 will be, so then A4 will be, this is 5, it'll be 5 plus the 7 minus the prefix sum, which is 6 right now. So you can see that you get the 1. So yeah, if you do 5, you get 6. And then A5. So then A5 will be 12 plus 7 minus, well, this is essentially 12. So you get A5 to be 7. So then when you go to the next one and you take 10 plus 7 minus, well, you added basically a 7 to this, so it's 19 now. You'll get 17, you'll get -2 for the 10 one. So here's the thing to notice is that this value here is equal to the first value. So it doesn't exceed the maximum value, which means that it doesn't change the maximum value to be equal to it. Well, it doesn't change the maximum value. Huh. So if it had changed the maximum value, that would mean that you'll be taking the prefix sum plus the a value, whatever it is, a5, minus a5, right? If you're changing it, and that has to be equal to b5, which means that b5 has to equal prefix sum for that to have worked, which just seems kind of highly doubtful. So I guess the reason, I mean, I printed out some stuff here too. Like you can look, like here I had, I think think I had this at 10. So for this one, you can see that it starts with the 11, since 11 is the largest difference, which is 10 minus -1 is 11. So you get this one where, and then you keep adding up and it keeps updating the perfect sum. So the perfect sum will be like -1. So the perfect sum will be um, oh no, sorry, this is the BI character. So the prefix sum is the first one. So the prefix sum starts at 11 and then it goes 10 because it decreases by 1 and then it increases by 1. It basically follows whatever the differences between these two values, right? So now it adds 4 to this one. Um, Actually, let me print out what AI is. So yeah, so does this one, and then this one is 4. Um, and then this distance here is 7. So it sets it to the 7, and we get a prefix sum that's 23 now. It's quite a bit larger than 11. It's large enough to where, it does this. And then now we can start decreasing because now we're in a point where we're monotonically decreasing here. So they're all negative and it just keeps decreasing the prefix sum, so that the difference between the prefix sum and the first element, which is the max element, the prefix max, is equal to the B character. But we have to keep decreasing this prefix sum because this value, the B, keeps decreasing until you get to the point where, the prefix sum can be under 11. Like the prefix sum can be negative as well. So it can go all the way under 11 and it's fine. But then if you have a difference that is 10, you need to be able to take this number and add to it a number without changing the 11. It's fixed so that it goes right above it like this. But I mean, let's say you started at 0 and let's say these are all negatives. So let's say it's just negatives. I'm actually just kind of exploring the solution because I'm now curious why it worked. Like I saw the pattern, I was like, okay, it might work. It worked. But now I'm just kind of like, how would you prove it? So for instance, setting to 11 won't work, but why does setting to 11 not work in this case? Because if you set it to 11, it starts out like this. So it says the first element to 11 and the previous 7 and the previous max is this. Then what happens is well, technically, yeah, then what happens is it goes to this point, right? Okay, we have to decrease by 1 because this is -1. So we need to be 1 less. Cool. Okay, we still need to be 1 less, so there's no decrement, so we need our current element to be 0. Okay, we need to be even smaller. So let's decrement it by -4 to get it to be -5. Basically, the difference between these is -4. The difference between these is -7, so we have to decrement by 7. If you decrement by 3, we have to decrement by 5, decrement by 5, decrement by 1. At this point, the prefix sum has now decreased all the way to -15 and 11. But then we somehow need to achieve 10. And you can tell the only way to achieve 10 with this prefix max is by getting this to be equal to, is by getting this number here to be equal to 21, right? I somehow have to convert the prefix sum to 21. But how could you possibly do that? You've been decrementing it this whole time. You've been decrementing it so much that you're 26 values under. Well, think about it. The difference between that, your 26 values under, and then the difference between the -26 and the 10, that difference represents how much I need to change it. I need to change it somehow by that much. But the only way to do that is, well, the distance between those two is like 36. So the only way is to add 36. So I somehow need to add 36 to this, but without changing the prefix max, because I want it to be 36 minus 11. If I if I say, okay, I need to add 36 to it, but then it just sets the prefix max 36, then it's not gonna solve it. So if I just so when it says 36 here, it changes this number here as well. And so because of that, you actually end up getting something that's still like negative 15. It still is not exactly equal. But if you set this equal to the largest distance, then it works because you start with 36, and now you're just going to keep decrementing. But by the time you decrement down here, you're negative 26 off, so it's 10 and 36. But you can always add to the 10 with a number that is not greater than 36. In fact, all I have to do is add 36 to this to be able to get 46 and to have it go over it. So I guess it makes the problem easier. Like sometimes these constructive problems, it's easier to find a constraint, something that you can fix. And I guess saying that my prefix max is fixed based on the first element I pick. When I pick A1, um, I'm also picking the prefix max. It's going to be constant. It'll never be greater. And there's a certain way I can pick it so that I can find a solution where the prefix max will never decrease or will never be greater than that. But it's based on the distance between these two, in a sense, because I need to, at some point, whenever I'm moving between the elements in B, I need to increment by the distance, the difference between those two elements. So in that sense, when I increment, if I want my prefix max to be fixed, that increment cannot be larger than the A1 you pick. In that sense, it kind of makes sense. And I think there's probably a more mathematical proof as well, but I don't really have it right now. So I'm just gonna say like you can kind of think of it intuitively and kind of come to why this might work. I mean, really, I figured it out by just doing this example here and looking at this pattern here, and I was like, okay, yeah, it looks like it's just the maximum difference. Um, yeah. I mean, we can also look at yeah. So, anyways, following that pattern, you just find the max difference, calculate the prefix sum, do this formula here, keep updating prefix sum, and then yeah, just keep calculating AI. Um, I'm gonna look at the discuss because maybe they have a nice proof for this one. They say we want to construct any array as long as we can ensure that the maximum element never changes, we're good. And they say B1 always has to be 0. Define the max. Um, okay, and you can say this here. They say the first relation bi equals bi minus 1 plus ai when mi equals mi1 is particularly nice. Okay. They just say if the max doesn't change, you can do this. You can say the prefix sum minus the max equals the first relation that bi bi is equal to the previous element plus ai. Huh. Uh, so ai is just the difference between these. And that means as long as a1 is not smaller than any of these adjacent differences, the maximum won't change and the construction is valid. Okay. Yeah, let me mess around with this one a little bit. I think I see. So there's actually a nicer solution than what I came up with. Okay, let's do this as a learning opportunity. Right. Radio we go here. Oh. Oops. Okay, well, now it's not even working. Okay. Yeah, this is the relation. Okay, so first off, how do we get this? So we say bi equals si minus mi. Okay, well this part makes sense. This is just like obvious, right? It's the prefix max minus the prefix sum minus the prefix max. That's the definition of bi. But you can say this is equal to the previous prefix sum plus adding on the current value minus, and if you're saying the max doesn't change, you can just use the max from the previous one. And if you see here, this bit right here, I see this bit right here is equal to bi minus 1. So you can say bi minus 1 is plus ai. So you have this relation that bi equals, this relation that works if mi is equal to the previous one, which means that you set m1 and it's fixed for the rest of the array. Kind of like what I did, although I figured out in a different way. I was wondering if there was a math proof, and I think this is it. And then you can do that, and then you can solve for ai. You can just take bi minus 1, and then that solves for ai. So you can solve for any ai, but you need to make sure that since the prefix max depends on ai, you need to make sure that ai, so this is the reason why the prefix max and why a1 has to equal the maximum difference between two adjacent elements in the array, the B array. Okay, I'm actually going to clean up my solution then. So for my solution, okay, I have to go back to it. Here we go. Okay, so for my solution, I could have just done, instead of what I did here, I could have just done, I didn't need to calculate prefix sum. I could have just done this minus like that. I think so. And I don't even need this. And I just need to make sure that I set the first one to be this. See what it gives me on these examples. That looks right. Interesting. Okay, so okay, that's that one. Okay, so this one I understand a little bit better because I took my time after the contest, and I didn't solve it during the contest, but I figured I upsolved it. So let's go with this one. So array concatenation. Count the number of Boolean arrays with A zeros and B ones such that the following holds. Let A be the Boolean array and AI be equal to the subarray of A1, A2 to AI. Concatenate A1, A2 to A plus B. So, and call this array B. The number of ones on odd and even index in array B are equal. And you want to count the number of ways that this can happen. You want to print the answer modulo. So it's a bit of an abstract problem. But the example here clarifies a little bit. So if given the array A, it just says if A was this 1 0 1 0, then array B becomes this. You concatenate the first subarray or the first prefix array, let's say, and then you concatenate the second one, which is 1 0. Then you concatenate the 1 0 1. Then you're going to concatenate the 1 0 1 0, and you end up getting this Boolean array. So, all right, so how do you solve this one? Okay, so why is okay? Okay, so for this one, you're given A zeros and B ones, and you know like the total size of the array is going to be A plus B. So you can say N is A plus B. And you basically want to concatenate these together. So the first place I started was looking for how I can count the number of zeros and ones. Or not even looking at it, but just saying like, suppose this index is a 1 in the array. Then the question is how many zeros or how many odd and even indices will it be in the array that you concatenate, the B array. And so just taking like the example of one like this, let's say you have, so this is the, it's weird that it doesn't work. Control Z doesn't work. Okay. It's weird. Okay, so you can have the array be like this. Well, yeah. Suppose the array, suppose you have like the 0 at some location. Or let's suppose the 1 is here, okay? But let's suppose the array is a bit longer. So the size of the array has to be even, it says. So this has to be even, is one of the constraints, which is a very important constraint. So given the 1 here, it's at this index here it starts, okay? So the thing to notice is when you concatenate this, how is it going to work, right? So you would have already concatenated your first element. So instead of writing the value element, actually I'm going to write the index. So it's going to be A0. Then it's going to concatenate A0, A1, right? because if this is A1, A0, A1, A2, A3, A4, A5, then these are the respective elements at that index. So it concatenates the first one, then it concatenates, okay, this Control Z not working is annoying. Then it concatenates the A0, A1, and then it's going to concatenate A0, A1, A2, and it's going to concatenate A0, A1, A2, A3, and then it's going to concatenate A0, A1, A2, A3, A4, and then it's going to concatenate A0, A1, A2, A3, A4, A5. And if you look at the index for these, so you say this is index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18, 19, 20. So you look at this example and you do this. You say, I guess look at the third, right? Because I said the third index is where. So the third index appears at index 9. So first off, where's the first occurrence of each index? Well, A0 is at 0, A1 is at 2, and then this one's at 9, and then A2 is at 5. So like, where does the first occurrence happen? It's basically the length of it. Like, the length of the array here is 1. Then the length of the array that you concatenate here is 2. So then it's going to be 2 more. Then the array you're going to concatenate, it's going to be length 3. So then add 3 to get to your next index. So it's basically just you go from 0 to 2 because you add 2. Then you go from 0 or 2 to 5 because you add 3. Then you go from 5 to 9 because you add 4. And then you're going to go from 9 to 14 because you add 5. So with this type of property, you know where the first index that element will start at. So then what really will kind of it'll depend on is this is my 1 could be any of these values, right? My 1 could be at the A3, my 1 could be at the A2, my 1 could be at the A1, or it could be at the A0. But if it's at A3, for instance, two things to notice. The current length of the array is even length. And the reason why I pay attention is because this thing can vary. Because if it was here, the length would have been odd. But it can only be even or odd. And the start index is odd, right? So given that constraint, where does A3 go from there? So it's even length and it's starting at an odd index. So if you think about this, this is what will happen for like each time you concatenate with this array after the first time it appears. Since it's even length, if you have an even length array, that means whatever the index is right now, like if the index was odd, it's going to go to an odd index, right? Because if your index is 1 and you add an even number to it, you're still going to be an odd number. So you know that the next index will be odd, but you also know that is that if the length was even initially when it was odd, so say this is the length, this is the parity of the length, and say this is the parity of the index, it's going to be at an even length, then it's going to be an odd. Now that the length is odd, it's going to push the next one to an even index. And then it's going to keep doing this and then this will stay the same because it's an even length, and then it's odd length. And so you see that this index is going to keep oscillating between odd and even in this pattern. For if it starts in this configuration where it starts with an even length and it starts at an odd index. But like, does it matter that it starts at an odd index? What if it started at an even index? It wouldn't have mattered. It would have just, if it started at an even index, you would have just started at even, and it just would have been this. It just would have been like inverted. Um, there's another possible pattern, which is that you start at an odd length. So yeah, so another possibility is you start, the length was odd, right? Because sometimes the length is odd. Like for instance, up here, if we look at one specific example, like the length here is odd. So you're starting with an odd length for this one. So if that happens, you're kind of looking at a slightly different picture where you have your length starts out as odd, then it's going to go even, then it's going to go odd, then it's going to go even, and so on and so on. And so the index here, depending on what index it starts at, but let's say it starts at even, well, then it's going to go to odd. It's going to stay at odd, and then it's going to go to even. So, okay, slightly different pattern. And that's just going to repeat this pattern. So one thing for certain is that it's a repeating pattern of length 4. Here, here, and then here it will also be. So, given that there is something of interest to look into, which is we want to know the counts of even and odd indices. So given these patterns, let's say we have this count function that's going to be count even minus count odd. Okay. So then let's say we have the length, or let's take one of the patterns. So one of the patterns I first looked at is that you could end up starting with an even index. So this is the index that it's at. And then it stays on an even, then it goes to an odd, then it's an even, then it's an odd again, etc. This is for each concatenation. So let's just put the count here. So here the count would be 1 because we have 1 even and we have 0 odd. Now we have 2 even, so the count would be 2 and 0 odd. Now we have an odd count. So now it's going to be, at this point, it's going to be 2 minus 1, which is equal to 1. So we're going to, every time we see an odd index, we decrement by 1. So it goes on 1, then it goes to 0. Then even here, it'll just go to 1, and then 2, and then 1. So this pattern will keep continuing, this pattern here of the count of the difference between even and odd. And that's for this specific instance. But then the thing to realize is, what is the meaning of this? The meaning of this is, first off, this represents when you start with an even length, right? That's the thing that I have to say here. I have to say this is for when you start with a length that is even. This is the pattern. When you start with an even index, you could always have the other pattern, which I'll draw that one over here as well. You could have the pattern where you start with an odd index, and it will go like this. So it'd be like that. And so the thing that I notice here is that actually, if you start with an even versus an odd, they're just inverses of each other here. So okay, whatever. They'll come back later. But yeah, the crucial point is we're only looking at when the length is even. So that means we're looking at something like A3, for instance. Now, why A3? Like we're saying A3 is equal to 1. Why? Because that means you have A0, A1, A2, A3, and that is an even length value. Now, I don't know if it starts at an even or odd index. So I don't know if it's this one to the left or this one to the right. But regardless, it's going to be 1 or 2s or negative 1s and negative 2s. But there's another important constraint here that tells you what values of these are actually important, which is that a plus b is even, which means that this element here, this substring here could be a part of a string where it's, or it couldn't be this. This is impossible. Why is this impossible? Because 1, 2, 3, 4, 5, 6, 7, you have 7 elements and it has to be an even number. So okay, so that one's actually impossible. But you could have something like this. But what it means that it's impossible means that how many times are you going to concatenate A3? How many times are you going to concatenate this specific element? You're going to concatenate it for each instance in here afterwards, right? For each of these added elements. So you're going to actually concatenate this 1, 2, 3, 4, 5 times. And this string could have ended here, and then it would have been 3 times. Or it could have ended here, and then it would have been just 1 time. So it's always an odd number. So if you look back up here, if it's always an odd number of like how many concatenations. So as you're kind of going down in this array, this was like for each concatenation. So like this was the first concatenation, the second, the third, the fourth, the fifth, and so on. So if I label them, let me see, if I add that here, this is a 1, second, third concatenation, fourth concatenation, fifth, sixth, 7. And only the odd concatenations matter. That means only this values are possible. So you start noticing that it's always a 1 or negative 1 for this specific instance. When you have an even length, you're starting with an even length for when it's, I guess, it first gets concatenated. Like this is the first concatenation A3 is with an even length array. And then each additional concatenation, you're going to have an odd number of total concatenations, which leads to this pattern here. Now, what about the case of, those are even lengths. What about the one that's odd length, like this one, right? This is the odd length one. First off, how many concatenations will this one have? For an odd length array, it's going to have to be concatenated 2 times or 4 times or 6 times. Okay, so it's even. So it's opposite. It has to be an even number of concatenations that it will be involved with. So in this case, we're saying the length is odd. And so we're going to look at the concatenation. We're going to look at the index, and we're going to look at the count. So again, the index could start at, it only has 2 options, but let's say it starts at even. Well, the length is odd initially, so you know that this even is going to go to an odd. And now it's even, so you know it's going to stay the same. So it kind of follows the same pattern as before, where you're going to always see these 2s. The only difference is that it starts a little bit different. And then that will just keep going. And if you look at these counts, well, you have 1, 0, negative 1, 0, 1, 0, negative 1, and so on and so on. And the concatenation is, this is the first concatenation, the second, the third, the fourth, the fifth, the sixth, the seventh. What do you notice is that all the even concatenations is 0. So that was for if it started at even, but if it started at odd, it would have been the same thing. So, and I'll leave that one proof to do, but yeah, so you can see that this array here is actually, this array right here, if it's at an odd index, it is always going to be 0 contribution. So, or it starts with an odd length. So The odd length ones don't matter. Okay, so let's write this out here. Because this kind of simplifies things a little bit. We're kind of getting it down. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I have 8 elements. It's an even number, so this is a valid. This is a valid array where I'm just representing. I guess I didn't explain this way, but these are just representative of the elements with the index, so that I kind of know which element is like. But you can place a 1 anywhere in here. But the point is, if you place a 1 at any of these elements, you're going to get 0 contribution, right? Like as I showed above, you get 0 contribution because the total, because of 2 reasons, because the array length is even, the total array length. So that means you know how you have an even number of concatenations. And the even number of concatenations, the total count of even, the count of even minus count of odd, that difference is 0. That is, the count of even and count of odd indices is going to be equal. So if I put a 1 here, it contributes it's gonna have to be 0. Okay, so the only ones that matter are these. These are the only ones that are going to contribute. These are the only ones that are going to contribute a 1 or a -1, because these are going to be concatenated an odd number of times, as shown in this thing up here. That means that it's always going to be 1 or -1, really just depending if it started at an even or an odd index. Which, let's take a look at this. We actually can figure out what index these start at really easily, right? We know this one starts at 0, and then we know we add 2 to that. Okay, we know this one's 5. We know this one's 9. Because we add 2, we add 3, we add 4. Then we add 5, then we add 6, then we add 7, then we add 8, and you can keep going. We add 9, we add 10, and so on. So what I notice really quickly is for these ones that are important, the start index is 2, 9, 20, 35, 54. So it's even, odd, even, odd, even. And it just keeps going. So you can maybe generalize that this is a pattern here. And you can even maybe make an argument why this is a pattern. If you think about it, when you're at this value here, you're going to add an odd and then you're going to add an even. Right? It's going to be, you're going to add an odd and then you're going to add an even, which means the difference between these two is odd. Which means that these are always going to switch from even to odd, because all of the distances between each of these elements that are representative of an even length prefix array, right? This is 2 elements, 4 elements, 6 elements, and so on. All of them will have an odd length of distance between them. So if you take this odd plus this even, you get an odd length. So yeah, you know this is always going to be switching. So it's going to be even, odd, even, odd, even, odd, and so on and so on. So really, you can count the number of these. And just remember that if you start with an even, that means it can contribute a 1. You start with an odd, it can contribute a -1. So that is the contribution. And so what you can see here is we can count the number of index or positions where we can place a 1 and get a count of 1 or -1. Yeah. So so this is true. Count the number of index where we can place a 1 and get a count of 1 or -1. And we can count that really easily from up here because we know how many even odds there are. How do we know how many even odds there are? Well, right here, see this length is 2, and you have 1 even. So, and remember, your length can only be 2, 4, 6, 8, 10, 12, and so on, right? Because it has to be even length. So how many evens are there? Let's count the evens and odds, actually. Yeah, so let's just do it like this. Let's do it like this. So let's say our lengths are 2, 4, 6, 8, 10, 12, 14, 16, and so on. And let's count the odds and let's count the evens. So we know we have one here. We get our first odd here, and we still have just 1 even. We get nothing here, but we get another even. We get another odd here. I'm just going to fill this in, actually. We get another even here. Oops. Nope, sorry. We don't get an even here. We don't get an even. We get an even here, and we get an even here. So what you can notice is that the count of even is basically n. It's n divided by 4, but ceiling, right? That way, when you divide 2 by 4 and you take the ceiling, you get 1. When you take 4 divided by 4 and you take ceiling, you get 1. So it will go up as soon as it can. So 6 divided by 4 with the ceiling will be 2. And then you can see for the odd, it's going to be the floor division. So that way, when you take 2 divided by 4, it's 0. But when you take 4 divided by 4, it'll finally be 1. So that's how you can count how many positions there are for the odd and the even. And then the odds are going to be associated to 1. So we're going to associate these to counts of -1 and counts of +1 because that's what actually is important. And then I'm just going to say the count of zeros, which is the indices between those is going to be just n minus these, right? Those would be the positions where we can place a 1 where we will get nothing. So with these counts, you still want to solve the problem. Okay, so how do you solve the problem given that you're able to count these values? Well, you're given B1s and you want the ones to be equal. You want the indices to be equal, right? Which means that you want the count of -1 or let's say X represents is how many positions you picked. It's the positions with that are going to contribute -1. That is, they have one more odd than even index. And you have Y positions with +1. And so these can only be up to, so X has to be less than or equal to C minus 1, and Y has to be less than or equal to C1, because that's like the total number that I can pick, the total number of positions. So, but here's the thing. These are going to be equal. That is, I have to pick, if I pick four positions, if I pick 4 positions where the value is -1, I need to pick 4 positions where the value is 1 so that they cancel. And then whatever remainder, I'll pick as a value of 0. So I'm going to try to do an example here. So let's say C1 is 4, C negative 1 is 5. This is not possible. This will always be larger than that one. So C5 is this is this. C0 will be whatever n is minus, yeah, minus these two. So it could be something like, well, this could be from, well, this is from something very specific. I think this is from, um, 5 plus 4 is 9, so maybe 18. I think this is 18, but it'll be minus the 9. So yeah, it'll be something like a 9, let's just say. Not counting exactly. Say it's 9. So then I could pick x to be equal to 2, right? Why? Because 2 is less than these. So then if I pick 2, and these are the number of places I can pick, how can I count the number of ways I can pick from these, right? These kind of combinatorics. Well, it's going to be 5. I can pick 2 from 5. I can pick 2 of the positions and place a 1 there, right? So I'm saying I'm placing this many ones. Or this isn't how many ones I'm placing. I'm actually placing 4 ones. But this is I'm saying I'm placing this many ones in a location where um where it will be 1 and negative 1, right? So it's kind of saying how I'm distributing the ones in the array, in the A array, but it's a bit abstract, I know. So you have the A array. It's a bit abstract, but it's like, where am I going to place the ones, right? And I'm placing them in these positions where it contributes a 1. And how many ways can I do that? I can pick 2 from 5. And how many ways can I do it for this other one? I can pick 2 from 4. And then and then you just have to do the remainder, which is how many ones do I have remaining, which I don't know whatever B is. So whatever B was, like, I don't know how many ones you had to place, but assumedly it's greater than 4. It's greater than 2 times x. So then you do this, and then you subtract. Well, you can't pick the ones you picked over here, so you have to subtract the 4. So that's remainder of B's. How many positions do I have to pick these from? It's basically C naught, right? Like, that's how many positions I have. And so these will contribute 0. Um, so now I'm going to write out the formula here, which may seem a bit, hopefully it's clear. So if you say x is 0, so x can go up to b divided by 2 floor division. And then you want to count the number of ways for each x. So again, like the x was fixed up there, you're going to pick from c positive 1, the count of these. You're going to pick x from these. And you're going to pick from this x as well so that they cancel each other. And then you're going to pick from what the remaining, which will be n minus c1 minus c negative 1. And then the remaining elements to pick from those. And then, yeah, that's basically the formula for the answer. And I don't know, it's kind of hard to go through the proof of that one, but yeah. So basically, I do have helper functions like ceiling, floor. I'm not going to this one, but inverse, the multiplicative inverse mod or something. And then of course you have the factorials. And then this is what calculates the combinatorics, is picking R from n elements. What are the number of ways to do that? So this is counting 1 and counting 2. So this is counting how many contribute a positive 1. There are more evens than odds. And this is the ones where there's more odds than evens. So again, it's dividing by 4 using the ceiling and the floor as I went over. And then you're going to do the answer. So then for each I up to the floor of b divided by 2, suppose I pick I from these 2 sets of elements, and these are the numbers. So how many ways can I do that? And then suppose I pick the remainder, which will be this b minus 2 times I, and then these are the number of elements you have that will contribute 0. And then you just sum that up and modulus it. Okay. Yeah. So Yeah, that's the approach to it. There's one other thing I'm going to say about this that came up for me, which is that the only reason this solution works is because you have three categories. So three categories. What I mean by that is you only have an array in a sense. Like, okay, let's say you have an array, but your array only contains values 1 or 0, 1, and -1. And so the question is, how can I pick k elements from an array of n elements such that the sum equals to 0? In a sense, this is what you're doing in this problem. But in this problem, when you reconstruct that array, when you define it a certain way, you reduce it down to that the array only contains these values. In fact, I actually know how they would distribute it. It starts with a 1, a 0, right? This is if you say the count is even minus the count of odd. So for the next index, it's 1, then it's 0, then it's -1, 0, 1, 0, -1, right? This is the pattern. So this is literally the problem. I'm just restating it in a different way and showing how it relates to other problems. This is the actual array you can reduce it down to, an array of just 0, 1, 0, and -1s. And basically you want to figure out how can I pick n elements, how can I pick k elements from here such that the n elements as a sum equals to b. By the way, for this problem, what is k equal to? It's equal to b. It's the number of ones, right? Because I want to pick these ones such that they sum, so they sum to 0, right? So, right? And so you can solve this with using combinatorics. But the only reason you can do that is because there's only 3 elements in here, and because there's a 1 and -1, and there's zeros. If this array contains like any values, so like 2, 5, 6, -1, -2, 0, 0, and then you want to do the same thing where you want to get the sum equal to 0. If k is equal to 2, well, first off, let's do the easiest one. If k is equal to 1, then obviously the only solutions is the zeros. And if k is equal to 2, then this reduces to a famous problem called the two-sum problem, which is pretty easily solvable with like a hash table and everything. It's like a problem you can find on LeetCode, really popular one. So it reduces to the two-sum problem. And what I thought is interesting about that is, okay, because you want to get the sum equal to 0 and you want to get two values that sum to 0, right? But in this problem, it becomes more complicated because k could be anything. It could be greater than 2, right? So k could be 6. Well, that's harder to solve now. You can't, it's not the two-sum problem. It's going to be more complicated. You have to somehow be able to pick 6 elements from here that sum up to 0. I mean, you could even think like basically it's like, how could I pick elements of this sum to some sum? It doesn't have to be 0, but in this case it's 0. So that problem's kind of unsolvable. The only reason you're able to solve this problem is because your array only contains 3 integers. And 2 of those integers like cancel each other. It's like a negative x and an x. And the other ones are neutral, a 0, so they don't really contribute. And that allows you really that's kind of like a property that allows it to be rewritten into this formula here, into this combinatoric formula that is also a very simple structure. But that's just an observation I made. So I was like, when I was solving it, So that's it. So I just went over the first four problems like I said I was going to do. And that'll be it. It did take a little longer than I expected. I think this one, I guess the prefix suffix min max, I kind of solved it without really having a good proof. So I guess I kind of struggled getting the proof of that one. um, so yeah, well, that's interesting. All right.